This is the another part of pipeline architecture. Here we will discuss about the exercise and different types of example of pipeline architecture with data hazard. So let's know firstly data hazards. What is data hazard? Mainly data hazard is dependency, like um, uh, when one instructions depend on another instruction. That means data hazard occurred when an instruction depend on the result of previous instructions and that result of instruction has not yet been completed. Whenever two different instructions use the same storage locations, it must appear as if it is executed in sequential order. There are four types of data dependencies. First one is read after write. That means here after write you have to read, and the second one is read write after read. That means firstly you need to read, then you have to write, and the third one is write after write. That means you can write after write, and the fourth one is read after read. That means here you can read after a data read. The first data hazard is read after write, and it's also known as through dependency or flow dependency. It occurs when value produced by an instruction is recorded by a subsequent instructions. For example, here has two instructions. First one is addition and then second one is subtraction. In addition instructions, you can see the register value R2 and R3 will be added, and then the value will be stored at R1. That means the value of R1 is write first, and in the second instructions you can see here happening here have a subtract instruction. So the R4 register will be subtracted from the register R1, and finally the subtracted value will be stored at R5. But the second instruction cannot execute the subtraction because firstly need to write the value of R1 in the instruction of addition. So it is the example of read after write. That means here you need to write first and then you can read. So it's also required to handle this hazard. Here if you follow the figure, here B tries to read a register before A has written. So before A written, B can be tried to read and it gets a old value. This is common and forwarding helps to solve it. And the second example of data hazard is write after read. It is also known as anti-dependency. This hazard occurs when the output register of an instruction is used for write after read by a previous instructions. For example, here has two instructions. First one is addition and the second one is subtraction. If you follow the first instruction, you can see the addition will occur with two register R1, R2, and then it is stored at R3. And the second instruction is subtracted with the value of register 4 and register 5, and then it write a new value in and that is stored at R1. So in the first instruction, R1 carry a different value, and after completing the first instruction, then R1 write a new value for the subtraction. So here write after read. So read is happening in first instruction and then write at the second instruction. If this if you follow the figure, here B tries to write a register before A has read it. So if B can do it do write before the instruction A is read, then in this case A use the new value, so that will be incorrect value. And the next example is write after write. That means you can write a value before anyone write. So it is also known as output dependency. This hazard occurs when the output register of an instruction is used for write after written by previous instructions. For example, here add is write a value for R1, and subtraction is also write a value of R1, and it is not so when that will be changing the value in both instructions. So this is an example of write after write. If you follow the figure, here B tries to write an operand before A has written it. So here B will write first and then A will write. After instruction B has executed, the value of the register should be B's result, but A's result is stored instead. This is only happening with pipelines that write values is more than one stage. And the next example is read after read. It occurs when the instructions both read from the same register. For example, the first instructions of additions read the value of R1, and the second instruction also read the value of R1. Since reading a register value does not change the register value, this read after read. So hazards that does not cause a problem for the processor. Now let's know about the handling of data hazard. There are various methods. The first one is forwarding, the second one is code reordering, and the third one is still insertion. The forwarding is adds a special circuitry to the pipeline. This method works because it takes for less time for the recurred values to travel through a wire than it does for a pipeline segment to compute its result. The code reordering. We need a special type of software to reorder code. We call this type of software is hardware dependent compiler. And the final one is still insertion. It inserts one or more installs into the pipeline, which delays the execution of the current instructions until the recurred operand is written to the register file. But this method decreases pipeline efficiency and throughput. This is the instructions and clock cycle depend on the pipelining instructions that you already know from the previous class. Here has 5 steps for each instruction. These are IF, that means instruction phase, ID, that means instruction decode, EX is the execution, MEM is the memory, and WB is the write back. And this is a simple example. Here have no dependency of one instruction to another instructions. This is an example of data dependency. Here has three instructions and with some registers. If you follow the main instructions, the 3 instructions in the left side of the table, you can see here R2 is a common register that is used in free instructions, but here has no dependency of this register because it is just a read after read. But here have another register R4, and this is there has a dependency of instructions 3 on the instructions 2, because the instructions 3 cannot execute before the write of the instructions 2 in the for the register of R4. So here happening 2 still. The third instruction cannot use data at R4 until new value is updated. This is a pipeline hazard, and pipeline still is a delay in execution of an instruction. So if have any dependency of one instruction to another instruction, that's called the data hazard of the specific register. And the waiting time or the delay time in execution for the data hazard is called the pipeline stall. Here I add some data hazard example by after simulations. Here has an instruction set. If you follow the left hand table, you can see here has 4 instructions. The first one is integer types additions, then subtraction, then another subtractions, and finally is multiply. And here has the register. So the first instructions just execute simply from the IF to WB right, instruction phase to write back, and the second instruction also works simply from the instruction phase to write back, and as well as the instruction 3 is work simply, but the instructions 4 cannot work simply because it has a delay time. that means here occur an hazard for the register R4 with the instructions 1 and 3. Okay, the instructions 3 depend on the instructions 1 for the register of R4, so it cannot read R4 before write back of R4 in instructions 1. So here occur a stall time, delay time, and this is the stall. There is another example of data hazard. Here has 3 instructions, and if you follow, you can see that here has two types of hazard happening here. And the first one is with the instruction 0 and 2 for the register R1, and the second hazard is with the instructions 1 and 2 for the register of R4. That means here the instructions 0 and 1 can execute simply, but instruction 2 cannot, because it have the delay time, and it had the delay time because the instruction 2 cannot execute before the write back of register R1 and register R4, because it depends on the instructions 0 and 1. So here happen 2 stall time. Here is another example of data hazard, and in this example have 3 instructions. In each instruction is need 1 clock cycle, we already know, but in this example for the divide instructions we set clock cycle 2. That means it needs 2 clock cycle time for execution of divided. So that here occur 2 potential hazard. The first one is with the instruction 0 and 2 for the register R1, and the second one is with the instructions 1 and 2 for the register R4. And here happen 3 delay time, that means 3 stall time, because the instruction 2 depends on instruction 0 and 1. Here instruction 1 needs to execute 2 CPU execution times. For that it needs 3 stalls time before write back of R1 and R4 instruction 2 cannot execute its computing. Maybe you guys think that how I simulate these tables or instructions and how I decide the stall time for those instructions. So here I add a link for simulate pipeline processing. This is not a downloaded software, because this is developed by a university. You can access this software through this link. You can execute your instructions from the website, but you can install or you can download this software. So try it, and I will provide you another Word file for the guidelines of simulating. That means how can you execute this software, and how can you find out your result. So please follow the attached Word file that I will add you in the class. Thank you.